thank you for inviting me. It's a pleasure to be in Denmark. I've got 3 apologies to start with. Firstly, my colleague Dietmar Koekemann is ill and can't be here. Secondly, you'll have heard that we've got a thing called Brexit. We always feel like we have to apologise for that. And thirdly, I speak in English. I can't speak Danish. It's always impressive when I come to other countries to see so many people speaking and writing in what's essentially a second language. I think it's worth saying some things about England before I start my talk. Aside from Brexit, the UK, you may not know that the UK is actually 4 countries. So I'll be talking about England, and I won't be talking about Scotland, Wales, or Northern Ireland, which all have separate education systems. They're really different, and in particular, Scotland is really different. England is bigger than Denmark. We've got 60 million people in England, and about 3,000 secondary schools, and about 20,000 primary schools. So rather bigger. We face similar problems, I guess, having just seen that, the talk that Thomas has just given. Our kids in England find multiplicative reasoning and algebra really, really hard. They come out of school not really seeing the point and not really being able to use these powerful tools that we have. And in England, we spent a lot of money on this. We spent a lot of money at the turn of this century, initially on primary mathematics and later on lower secondary mathematics. We're in the process of spending, and I apologize if I get the calculation wrong, something like 2 billion kroner just on maths at the moment in England to improve mathematics in schools, but also in upper secondary pre-university mathematics. What I'm going to talk about today is some work that Dietmar Koekemann, myself, and Margaret Brown started about 12 years ago. It was initially funded by the ESRC, which is one of our big research councils in the UK. So it funds straight research. This was funded as part of a bigger, wider program to improve participation in STEM subjects post-school. But most of the projects were focused on improving mathematics or science subjects in school. It's later been funded by 2 organizations, the Nuffield Foundation and the Education Endowment Foundation. Nuffield Foundation are a charitable trust who are interested in research that has an influence on practice. And the Education Endowment Foundation, I guess none of you have heard of this organization because it's a UK organization. It has really transformed education and educational research, in some ways for the better and in some ways for the worse. If you haven't looked at the Teaching and Learning Toolkit, it is really worth looking at that. It's a league table of interventions and strategies that can be used in school. In England, 70% of our head teachers use that tool. So it's really transformed how people communicate research in education. The Education Endowment Foundation are less interested in research and more interested in practice, and they've funded a large-scale trial of this work. I'm going to. How do I make this? Is that there we are. So I'm mainly going to talk about this first project, increasing competence and confidence in algebra and multiplicative structures. And I'm mainly going to talk about the pedagogy of didactics around the intervention, and specifically the lesson aspects of the intervention. The intervention also has a professional development aspect. And this was a design research project, and there's some other bits of the project that I'll talk about in a minute. I'm also going to draw a little bit on 3 reviews that I've conducted for various funders, in which we've reviewed the evidence of what evidence, what basis, what strategies might work in various bits of mathematics. Upper primary and lower and secondary, early years and lower primary, and with low attainers. And in some ways that's made me think differently about pedagogy. In some ways it's made me think made me rethink some of my ideas. So the ICAMS, increasing confidence and competence in algebra and multiplicative structures, it's got several phases. The first phase was a nationally representative cross-sectional survey of Year 7, Year 8, and Year 9. Another apology. We don't have grades in the UK. We talk about years, and we use different numbers to you. So I'll read that again. Nationally representative cross-sectional survey at grade 6, grade 7, and grade 8. Why we do that, I don't know. We also had a little longitudinal survey looking at lower secondary, and this focused on a study from the 1970s, which Margaret and Dietmar had been involved in, the Concepts in Secondary Maths and Science project, which was one of the first projects to document children's understandings, and in particular common misconceptions in secondary. And we focused there on algebra, ratio, number, and fractions. And we focused on those things because, if you remember, our project was centered around STEM participation, and we saw those as crucial to STEM participation. That then led to the design research study, which I'm going to talk about, which was developing an intervention. And we centered the intervention around formative assessment, although I'm not really going to focus on formative assessment today. That then led to a small experiment, a small quasi-experimental study, which showed some promising results. And that led to a large effectiveness trial involving 109 schools, randomly assigned to a control and a treatment group. Unfortunately, I can't tell you the results because I don't know them. It's being independently evaluated by a team of evaluators from Manchester, and they haven't published the results yet. So I really don't know if it works. On past evidence from these large-scale trials, probably won't show great results, but we'll see. And currently, we're working on primary-secondary transitions in the north of England, using the lessons to enable primary teachers and secondary teachers to communicate about mathematics. And perhaps it may surprise some of you, it may not surprise others. The primary teachers seem to be better at it than the secondary teachers. And that raises an issue that was what we were trying to deal with. How can we enable secondary, and in particular lower secondary teachers, to teach maths a little bit better? Because we know from our research that actually that's where mathematics drops off at lower secondary. Now, firstly, the results, it's interesting to look at the results from our national survey. I'm just going to show you some results on algebra, and I'm going to show you the facilities of the items on algebra, and it's a comparison of kids in 2008, 2009, with kids about 30 years earlier in 1977. Green are items that have increased, and red are items that have decreased, and then there's some items in the middle that are uncolored. There are no green items. In fact, almost all the items had reduced. That was a shock to us. It was a shock to us because let's think what's happened since the 1970s. There's been a vast increase in the amount of research on mathematics education. there's been a vast policy focus on mathematics education. And I've just told you, we've spent a lot of money in the UK on mathematics teaching. It's slightly worse, actually. This sort of evidences the attainment gap. These are the proportions of students who had grasped, basically, primary mathematics by age 14 in the 1970s. So something around 5 or 6% at age 14 hadn't grasped all of the basics for secondary mathematics education. What had happened in 2008? In algebra, it doubles. Decimals doesn't quite double, and ratio, it doubles. In fact, we were most worried about decimals. Why were we most worried about decimals? Well, let's think what the world was like in the 1970s. In the 1970s, we just introduced decimal currency. Kids did not have calculators. They did not have digital watches. It was a world in which, when kids were presented with a problem involving decimals, they'd say, I'd rather use fractions. That's a very different world from the world that we're in at the moment. And yet, that their understanding of decimals had reduced that tail, I guess, of kids who really hadn't grasped primary mathematics regarding decimals had increased from around 6% to around 11 or 12%. So that's a really serious problem. When we looked at the items which had increased the least, they were measurement and number line items, and the ones that had increased the most, they were multiplicative reasoning items relating to aspects of place value. So it was a multiplicative reasoning problem. So what can we do about that? Well, actually, it's worth looking at the textbooks, because we went back and looked at the current textbooks, and we compared them to the best-selling textbook in the 1970s. So here's the current English textbook, and this is looking at the first set of lessons that introduces straight line graphs. So you can see we've got find the gradient, write down coordinates, write down the equation of the line, and here's the advice to the teacher. Emphasize that they only need 2 points, with the third acting as a check. So a very kind of procedural idea, and this isn't about straight line graphs. This is really about drawing straight lines, isn't it? It's not really about drawing straight line graphs. Well, when we looked at the best-selling textbook from the 1970s, the School Mathematics Project textbook, it's quite different. So they introduced this using a kind of realistic context. It was a fairground attraction. They presented several graphs in which you gradually put in more points. And here's the advice to the teacher. Immediately a line is drawn, we are attaching meaning to the intermediate points, and we must satisfy ourselves that each point of the line satisfies the relation. Is it true that for every point on the line, the second coordinate is always 3 times the first coordinate? That's a really different advice to teachers. So it may be that all that money we've spent has been spent on quite the wrong things. It's worth looking at some of the answers to that problem. And typically in the UK, we've contrasted transmissionist teaching with connectionist teaching, and one of the people who promoted that was Malcolm Swan in this book, Collaborative Learning. And there's been a lot of focus on the notion of transmissionists being bad and connection as being good, that's led to something of a backlash. So I guess none of you have heard of Craig Barton. He's a very big name in England. He's got a website called Mr. Barton Maths. He organizes the tasks associated with our main teacher's professional journal. He has many, many followers on Twitter. And he used to be someone who promoted problem solving in classes. And you can see from the title of this book that he's changed his mind. How I Wish I'd Taught Maths. And he's promoting an idea called direct instruction, which has become very popular in the UK. Direct instruction, Engelmann's direct instruction in particular, from the US, which is a kind of scripted approach to teaching maths. It's been very influential with other people. Here's a quote from someone involved in education in England, and you'll see who it is in a minute. The PISA results from last year serve to confirm that teacher-led instruction is more effective than child-centered, inquiry-based approaches. Project Follow-Through is to this day the most expensive piece of education research ever carried out. To my shame, I hadn't heard of Project Follow-Through. Who has heard of Project Follow-Through? It wasn't a research project. So it was a development project in the United States in the 60s and 70s. And it did do direct instruction along with other things. Throughout the 1960s and 1970s, teaching approaches were measured across the United States. Direct instruction, a teacher-led program, comprehensively outperformed a multitude of child-centered approaches. The evidence must constrain education experts. That's us. The recommendations must be evidence-based. As education ministers, we have a vital role, and I even say a duty, to base our policies on sound evidence, not fashionable experimental theory. And as I hope I've made clear, I believe the evidence is overwhelming. And that is our schools minister. Our schools minister is now telling us how to teach, and he's telling us that we should use direct instruction. Somewhat surprisingly, the evidence partly supports that. So in our reviews for the Education Endowment Foundation and the Nuffield Foundation, we carried out meta-analyses, both straight meta-analyses and meta-analyses of meta-analysis. And at the top there, you can see explicit and direct instruction. It's not got the biggest effect. I mean, actually, the biggest effect is associated with self-instruction, which is a kind of set of reminders to kids. But it's got the best evidence. It's got the most studies. The box is bigger, and the confidence intervals are smaller. The effect size there is about 0.6. That is a big effect size if you could achieve it. And this has made me rethink what this might involve. In fact, I should make clear that this is not just direct instruction. It's a whole gamut of things that we've labeled under explicit teaching. And we've used the term teaching because instruction means something very different in the UK to what it does in the US. We normally talk about teaching as a good thing to do and instruction as being a bad thing to do. But it also it doesn't just involve direct instruction. Explicit teaching emphasizes carefully constructed explanations and structured practice materials which have usually been designed and evaluated by expert teams incorporating both conceptual and procedural aspects of knowledge, and it usually involves some feedback. And now what I'm going to do is talk about our ICAMS materials and reflect on the pedagogy and didactics of that, and to reflect on how we have tried to make things explicit, but not to do quite the direct instruction method. It is instructive, though, to look at some of the ways in which direct instruction or explicit instruction will not work. And this is really important. Actually, direct instruction, contrary to what our minister says, is not a panacea. It's one tool in our armory. Now, the green dots here represent meta-analyses for explicit or direct instruction, and the blue dots represent meta-analyses for manipulatives and representations. So explicit and direct instruction broadly appears to be more effective than using manipulatives and representations. Turns out that's not quite the case. So in Kira Carbonell's meta-analysis, she separated out three outcomes: retention, problem solving, and transfer of ideas. And she looked at what happened when you taught manipulatives with explicit teaching, what she termed high instructional guidance, where the concepts, the mathematical concepts, were directly connected to the manipulatives. So, for retention, it was higher, as high as the highest explicit instruction. For problem solving, it was even higher. For transfer, explicit or high instructional guidance didn't help at all. What can we say from that? Initially, kids need some help to connect manipulatives to the mathematical ideas, so that they know how the mathematical ideas relate to the way the manipulatives are being manipulated. But once it comes to the point in which they need to transfer those ideas to different contexts, to different aspects of mathematics, they need less instructional guidance. They need to do that work for themselves. So ICAMS. ICAMS drew on formative assessment, misconceptions, of course. We thought the misconceptions work had been forgotten. Realistic contexts, the models of, models for work, connectionist ideas, and purposeful dialogue and collaboration. I'm not going to talk about that in any sort of detail, because I guess that stuff is really very familiar to you. We had a set of design principles, help teachers to use formative assessment, highlight students' misconceptions, set mathematics in realistic and intriguing problems, use models and representations productively, make connections explicit, and enable purposeful dialogue and collaboration. I'm really going to talk about that issue about explicitness today. So, our design problem. Well, here's Alan Schoenfeld, and I think this kind of illustrates the design problem that we have. He says, I can tell you, before this class starts, how things are likely to unfold, down to an extremely fine level of detail. It's not that I follow a rigid plan or course the students into it. There are many branch points and contingencies. However, I know what many of them are, and there are a few surprises. Mathematics classrooms for experts are relatively well understood. Yet it appears really quite difficult to communicate that expertise to our teaching workforce. So the design problem might be conceived in terms of didactics and pedagogy as making student learning explicit to teachers, making mathematics explicit to learners, and facilitating students' or learners' engagement via purpose and utility. And here I use Janet Ainley's and Dave Pratt's notion of purpose and utility, so that we're making the value and utility of mathematics explicit. That, of course, sets us a teacher pedagogical content knowledge problem. Teachers need to know about learning. They need to know about children's errors and likely misconceptions. They need to know that you can do things in different ways. And they need to be able to take a task and connect it to the mathematics, what Barmount and the coactive group call coactive activation. Here's part of the problem. This is an item from our test, and it asks what is the calculation. It's not asking kids to do the calculation. It's what is the calculation. The cost of 6.2 litres of petrol was £4.86. What would the price of 1 litre be? And they had a multiple choice. Unfortunately, this was one of the items that had gone down. At age 14 in 1976, about 30% of kids got that correct, and in 2008-9 that had halved. So it's a kind of serious problem. As an aside, our minister quotes this as a reason why we should be teaching long division, but he doesn't understand anything. It's mad. All we got. I mean, you all know what the two options are, and you all know what the misconception is. Here's a graph that shows it shows facility along the totals against children's understanding. So we've got that along the x-axis we've got total score on the decimals test. So that's a kind of proxy for children's understanding of place value and decimals. And on the y-axis we've got the facility for different responses. So you can see that a lot of kids leave it blank. At age 14, a lot of kids leave this blank. At age 14, they are not asked to do the calculation, they're just asked to choose the calculation from a list. Only a few of them actually get the correct answer, but many of them, they divide the bigger number by the smaller number. And it fools them. What's surprising is that more of our kids are fooled now than in the 1970s. That, to me, is a kind of serious problem of understanding multiplicative reasoning. And here's an item from the CSMS test. It's actually a Karplus item from the 1970s. It's developed in Germany. And many of you will have seen it. It's Mr. Short, Mr. Tall. We measure their heights with matchsticks. Mr. Short's height is 4 matchsticks. Mr. Tall's height is 6 matchsticks. How many paper clips are needed for Mr. Tall's height? This hadn't changed, actually. We were surprised, given some of the other results. Hadn't changed from the 1970s to 2008. As we were designing the lessons, Dietmar and I were in a school in Basingstoke working with some teachers. And we were trying to develop some tasks that we could use with classes and teachers to engage kids in the problem of ratio, to get kids to understand what was going on with ratio, and to move towards multiplicative thinking. So we were working with a teacher called Jaco, and he said, well, we'll use Mr. Tall, Mr. Short. That'll take us 5 minutes, and then we'll do something else. 45 minutes later, after they'd spent lots of time drawing and talking and arguing about the Mr. Tall, Mr. Short problem, they decided the answer was 9. That's the correct answer. It took a long time. I thought it was sorted. They'd drawn lots of pictures. They told me it was 9. The kids had all thought it was 8 to start with. They all said it was 9 at the end. At lunchtime, they came rushing up to me because I was in the staff room. We'd been at the school all day, and they said, "What's the answer?" I was flummoxed. I thought they'd answered it. They said, they said. So I said, "Well, you spent 45 minutes. You answered it," and they said, "Well, it could be 8 or it could be 9. It depends on what the rule is." So it was the rule rather than all the justification that they'd gone through. It kind of demonstrates how difficult it is to engage students and to really change their minds. But they're not so wrong. I mean, so we can look at a ratio table, and if we conceive of the ratio table as multiplicative, well, we can see that it's 9. But if we think about it as an additive table, well, the answer is 8. So in a sense, that answer of 8 is, although it's wrong, we all know it's wrong, but it's a relatively sophisticated answer. And we can see that from our results. So this is the same graph as same type of graph. We've got the total score on the ratio test. So on the x-axis, we've got a kind of proxy for understanding of ratio, and on the y-axis, we've got the facility at that level. And you can see that actually very few of them give a blank answer, but some of them do. And you can see at this end, they're solidly for 9. They suddenly got multiplicative reasoning, but in the middle, the peak is around 20. They're doing quite well on the ratio test, yet they're still saying this is 8. So it does appear empirically that it's a relatively sophisticated answer, and I think it's useful to place that in this notion of the realistic mathematics education notion of developing a model of to a model for. We develop a model of contexts that can then be used for a model for using mathematics in other places. But it takes a long time to develop that model for, a long time and a lot of different contexts. This emphasizes the way in which we need to get kids engaged. So that Striefland talks about insightful reproduction of the system. So which is it? And so what I mean is we've got to connect that ratio table to other things. We've got to connect the ratio table to the sense of this being a ratio problem. And central to that, it seems to us, is the use of the double number line as a stepping stone to understanding the ratio table. So we can put the double number line vertically. We can then start to extract it from the context to make it more abstract and link it to the ratio table. And in our lessons, we tried to do that. Using examples from real life, realistic context. This is Westgate Close. So Westgate Close is quite interesting. This is Google Maps, and Google Maps, being American, is really weird. They show things in meters and feet, but meters and feet is great, isn't it? Because we've got a 10/3 relationship. I mean, we've got a really nice relationship, and look at Westgate Close. It's not bent. Slightly off, but it's not bent. We can start to use Westgate Close as a kind of move towards developing that notion of the double number line. So it gradually becomes more abstract. We've got some people on that. They've got their houses at various points along the line. So and gradually then we can start to introduce some really explicit instruction on how to then use that to build up a real sense of what that double number line means, but that is built on the double number line set in a model of a particular context, so that we've got something really strong to build on. And then, of course, we can use that model of in other situations where it suddenly becomes a model for. But remember Kira Carbonell's stuff? The issue of transfer is where we need to pull away the instructional guidance and let the kids do a bit of work for themselves. They've got to have some space in which to figure out that the same model, the model that they've developed in the context of Westgate Close, can then be used in another context. Here, another conversion context, but a conversion context involving money. And of course, then we can move towards other contexts that are not straight conversion contexts. So that's one way in which I think we need to be explicit, but being explicit doesn't mean telling the kids everything. Some aspects we need to tell them, and some aspects we need to be explicit so that they can get it. A real problem, and I was going to show you this on GeoGebra, but I haven't got GeoGebra here, is that many of the representations that we use are transparent and highly visible to teachers. So when we use something like the ratio table, or a double number line, or a Cartesian graph, teachers can see exactly what it represents. They can't remember how difficult it was to negotiate the meaning around those representations. And here we've used perimeter. Perimeter's often used in textbooks to support algebra. When you ask kids, they generally don't find the perimeter examples terribly helpful. They just say that's just a picture. I just add up the letters. Teachers said to us, this must be really easy. It became really difficult for the teachers when we presented them with the problem of what would this T-shape look like as the numbers became negative. And there are ways in which you can present ideas. It became a really knotty problem for those teachers. This problem, again, which is larger, 2n or n plus 2. I guess many of you have come across this problem. And Malcolm Swan has a problem based on this. 2n or n plus 2 is it always, sometimes, or never the same. In the CSMS test, this was a straight problem. It's those which is larger, 2n or n plus 2. Kids weren't given given the possibility, or the explicit possibility, of the correct answer. It depends. Any ideas how many of our How many of our kids at age 14 got this correct? I should tell you what the answer, what answer we're looking for. We're just looking for two examples. So we're looking for something like, well, 2n's bigger when n is 3, and n plus 2 is bigger when n is 1. Whichever, yeah. I'm getting confused now. 2n is bigger when n is 3, and yes, n plus 2 is bigger when n is 1. Any ideas? Yeah.
Well, I guess it would depend on what the possibilities are for answers.
Oh, they've just got this. They've just got this. Yeah. So it's just a straight question, and it's in the middle of an algebra. It's in the middle of an algebra test. Our teachers, when I ask this to teachers, they say, oh, it can't be very many. 50%. 5% of our 14-year-olds got this correct. That's... Sorry? It was giving two examples where it was different. So it would be 2n was bigger when n was 3, and they were the same when n was 2, or they were n plus 2 was bigger when n was 1. So it's not looking for an algebraic answer, so the correct answer was giving just two cases. So at age 14, so about 10% of our kids go on to do advanced mathematics. So half of the kids who were going on to do advanced mathematics were at age 14 not getting this correct. That seems a problem to me. Here's that graph again. On the x-axis, we've got the algebra score, a proxy for understanding of algebra, and on the y-axis, we've got the proportion who give that response. We've got a few blank responses, and we've got a whole range of other idiosyncratic responses, but the big response is, unsurprisingly, 2n, because multiplication makes things bigger. Now, of course, if you ask that question in different contexts, you can make it easier. You can, if you give kids, if you talk to a group of kids about this problem, they'll talk it round. They'll start to say things like, well, I don't know what number the teacher's thinking about. The n is a specific unknown that's in the teacher's head. They'll start to give cases. But this question at age 14 tricked the kids. So those kids really haven't kind of grasped the notion of variable at that point. And that age 14 really is towards the end of our school education. In England, we stopped teaching mathematics to most kids at the age of 16. And for most of the age 15 and 16, we aren't teaching them anything, we're preparing them for exams. So in a sense, this is, that 5% is as good as it gets for most of those kids. So it's a problem. We can make it easier. And this is not an argument that kids shouldn't be doing this, because of course they can engage with these problems. And this is one of the ways in which we've engaged them. This is the structure of our lessons. We have an assessment task, and you can see that the assessment task, which is bigger, 3n or n plus 3, relates solidly to that 2n or n plus 2 problem. And this was with year 7, grade 6 kids, so kids who are about age 11 or 12. Then that moves into a comparing expressions in context, a boat hire context that I'm about to show you, and moves back to looking at the initial task, 3n or n plus 3, and really trying to solve it using similar techniques that they've used in the comparing expressions. And I think there's two ways in which we do make things explicit to teachers here, actually. We make student difficulties explicit at the start in the assessment, and then build on that in the lessons. And between the lessons, we give them thinking time. Because the lessons are all connected, and because they don't take place at the same time, they've got thinking time to think and consider about student learning. So here's the boat hire lesson. Olaf is spending the day at a lake. He wants to hire a rowing boat for some of the time. This was before Frozen. So Olaf wasn't in Frozen. So it was an unusual name, and which is kind of deliberate. And Olaf has 2 boat hire companies. Freya's boat hire charges £5 an hour, and Polly's boat hire charges £10 plus £1 per hour. Whose boat should Olaf choose? Well, of course, we know it depends. And it's a realistic, not a real-life problem, because these kids can kind of grasp the idea of boat hire, but they haven't seen boat hire. Not all of them will have seen boat hire context, and they certainly won't have seen boat hire context using these charges. But it's a realistic problem in which the students can grasp some of the context to support their thinking. And I'm going to focus on 2 things here. One is making the power of structure explicit. And this relates to something from Thomas's presentation earlier, where he had 2 tables. One was, I think it was Luca had an ordered table and Sophia had an unordered table. I can't remember which way around it was. Typically, our teachers in England present students with a table that they've constructed, that the teacher has constructed. And it's usually a table that goes n, 1, 2, 3, 4, and shows the values when n is 1, when n is 2, when n is 3, and when it's 4. That doesn't allow kids to see the power of structure. So it doesn't allow kids the opportunity to see what added structure an ordered table produces on an unordered table, and what added structure an unordered table does in relation to collecting the answers higgledy-piggledy or in a random order on the board. So in this lesson, the teacher collects some of the ideas on the board in a random order. And then the teacher suggests, should we put them in a table? And the teacher puts them in this table. Because the aim is that some of the kids will then say, why don't you order that table? So that we make explicit the move from an unordered table to an unordered table. We make explicit the power of structure. What structure brings to then thinking about the commonalities in the steps. And secondly, we use, this is where we introduce the Cartesian graph. Very different to the introduction of the straight line graphs before. We're using expressions, not equations. So we don't have 2 types of symbol in each. We just have one type of symbol, and we don't have that problematic equal sign, which we know is problematic. And this, of course, is introduced as a model of the boat hire context, but we're developing it as a model for representing expressions and representing multiplicative relationships and algebraic relationships. And then we go on to represent that in different contexts. Here we have a context in which those common think of a number problems. What happens when we multiply by 4 and then add 5, or add 5 and then multiply by 4? And of course, we then get to parallel graphs. So we can use the Cartesian graph as a tool for solving and representing other problems. We're looking for a point when the kids will say, remember what we did with Olaf? Could we draw a graph? Which some of our kids have said. We think is highly unusual. So, I started by talking about the design problem in terms of didactics. And I've talked about ways in which we've made student learning explicit to teachers, made mathematics explicit to students, to learners, and thinking about that notion of utility, making the value of mathematics and the utility of mathematics explicit. And I think making mathematics explicit does involve some aspects of what that backlash has talked about, of carefully crafted tasks, of pedagogy, of really good explanations, and really crafted explanations, which I don't think we do very much. But it also involves using mathematics in different and related contexts. We can only generalize by using the models in more than one context and using them to illustrate and represent the mathematics. But being explicit really does involve more than just telling. We cannot tell kids that Mr. Tall and Mr. Short is a multiplicative problem. They have to have the space and time to see that and believe that for themselves. Otherwise, we're going to have kids who are excited, who come to us and say, is it 8 or is it 9? Kids need space and time to think about those problems. And teachers need space and time to consider student learning. I find it surprising how difficult it is to communicate what I think are quite simple ideas to teachers. And I think it's because I've forgotten the process of learning, just like they've forgotten the process of student learning. So I think we have to remember what it was like to learn not just mathematics, but to learn what it means to become a teacher, and of course a teacher educator. The direct instruction and explicit teaching literature focuses on practice. And I think practice and structured practice is really important. And we've de-emphasized that in England. We don't give kids enough good, efficient, and it needs to be efficient, time to practice. But I think that literature kind of ignores another problem. We need different contexts. Kids need different contexts in order to grasp that mathematics is powerful and general. It's not just practicing routines and abstract problems. They need to see that the mathematics is useful beyond one context. And I'll stop there for questions. Thank you.